Right, I think we are recording. Okay, the input signal that we were talking about previously, as some kind of input to ADC, it comes from it comes from a sensor basically that goes to signal conditioning. Okay, and it goes to ADC. Okay, so these are the input signal that we were talking about. The input signal that come from a sensor, okay, and it goes to signal conditioner. Okay, so as you understand, previously from here backward is all analog. Okay, so the input signal that we're talking about is some kind of analog signal. All right. Okay, so different industries, basically, they different devices, different industries, they work on different analog signaling. Okay, for example, in our watch system or in our clock, it goes up to 1.8 volts. Our phone, we have up to 3.7 volts. Any USB device, it goes to 5 volt. There are X device, they use 9 volt. Okay, some are using 12 volt, for example, in a car system. Okay, in a car system they're using 12 volt. Some industrial sensors, they are using 24 volts. In some heavy machineries, sorry, SEAVY, heavy machineries, they're using 48 volts. All right, so these are the ranges of voltage or analog signal. Okay, it goes from as little as 1.8 volt and as high as 48 volt. All right, so this is the analog signal that I am talking about. So your information can be as low as this, and some of the information can be as high as this, something like that. So these are the analog information that you need to work with this sensor. You need to work with this conditioner before you can pass on to A to D. All right. So again, you will also have to look at the analog to digital converter. Okay, as we may have covered or seen previously in the revision section in our lectures. uh, Sensors, they, oh my god, what happened? Sorry, sensors, they come in many operating voltage starting from 1.8 volt until 48 volt. Okay, signal conditioner also the same, they come in from 1.8 volt to 48 volt. Operating system the same as A to D, they come in 1.8 volt up to 48 volt. And of course, sorry, I put the arrow down for display system. Okay, normally works in 5 volt. All right, so this is the, I would say, the range of input signal that you will be dealing with in system of instrumentation as well as data acquisition system. All right, so each of these 1, 2, 3, 4, they have their own operating voltage range, which basically reflects the input signal that you will be dealing with. All right. For example, if your sensor is basically, so sensor is 1.8 volt, okay, and then you have signal conditioner, then you have A to D, and you have display definitely run using 5 volt, A to D. If you have, for example, your sensor is running at 1.8 volt, all right, and for A to D normally you run at 5 volt. In this case, I select A to D that runs in 5 volt, and you have a display which definitely run in 5 volt. Your sensor run on 1.8 volt, so you need to do some kind of amplification in the signal conditioning part, so that this 1.8 volt can be amplified to the maximum of 5 volt. All right, so you know what kind of gain you have to set here so that the system is basically matched. All right, so we are still discussing about the input signal, all right, in which I have shown you the input signal can basically come in, then basically takes a lot of voltage range, which cover from this range, and of course all these 4 elements, at least 3 of these elements, they can take any voltage range. At least you can confirm that the display unit, they have definitely operating at 5 volts. All right, so your input system that goes to ADC, is coming from sensor, also coming from signal conditioning. So that's the input range of the signal that you must be aware of, that you must be expecting, and you probably know what to do when you receive, for example, in this case, if I have sensors that work using 1.8 volts, what kind of amplifier I will need when my A to D is running at 5 volt, for example. There are also cases, where the A to D is using 12 volt, right? So if you have 1.8 volt over here, you need to figure out what the gain will be so that you can get a maximum voltage here at 12 volt. All right, so this is the input signal that you should understand, all right, when you work with any data acquisition system, all right, in which the input is basically representing the operating voltage of sensor, and also at the same time representing the operating voltage of the signal conditioner. Meaning that if your signal conditioner is at 12 volt, the A to D must be able to handle 12 volt signal. Okay, if your signal conditioner is working on I would say 24 volt, then your A to D must be able to handle 24 volt voltage swing. All right, so this is the signal that you are basically referring to. Any question, guys? Okay, because just now we were talking about input signal range, which can go from 0 volt up to the maximum operating voltage. All right, so that's the only possibility of input signal that you will be dealing with. All right, from 0 volt, when you have nothing to sense. For example, if you are sensing flow rate of any fluid in a water in a piping system, you are measuring flow rate. If there is no flow rate, your sensor will not be giving any reading, so you are working with 0 volts coming out. So your analog, your input signal now is basically at 0, because there is no flow in the piping system. Okay, This is your sensor, and the flow is going that way. If there is no flow, your what they call that, the sensor or the system will give you 0. The output of your signal conditioner will be 0. Okay, but if you start to have flow, you start to have flow, then basically the reading will go up. Okay, how much going up depending on the operating voltage of that sensor, of that signal conditioner. Okay, if the signal conditioner is maximum working at 12 volt, the input signal, the information from the sensors that comes into your system will go up to the maximum at most 12 volt. All right, so these are the information signal. All right, don't be confused between the operating voltage of the system and the information signal, because they are very much the same. All right, of course we understand voltage is 9 volts, 12 volts, that it's a supply voltage that power up devices. All right, if you look at voltage as a supply voltage, you are thinking about the voltage that power up device. At the same time, the same voltage is basically represent the information that you read from the sensor. All right, as being shown by this particular graph. When you have no flow, the information goes basically stays at 0. When you have some flow, you will have information going up. The maximum flow, for this piping system, they can give you maximum up to the operating voltage of that device, in which case, in this case, 12 volt. All right. So that's the input signal. If you don't have any question, I would to move to sampling rate, guys. Any question on the input signal? Any confusion? No?
Doctor, which means the operating signal is based on what you are measuring.
Yes, exactly. Minimum 0 when things that you are measuring is not moving, is not giving you any reading, is not responding, 0 volts. All right, in the analog form. And when the things that you are measuring is start to move, start to give some reading, you will see voltage rising. Okay.
Okay. Yes.
To the maximum of that operating voltage of that supply voltage for that particular sensor. Okay, if your sensor is operating using 5 volt from the USB, all right, so your reading from that sensor can give you from 0 volt up to 5 volt, and that's it. All right.
Okay, sir, but in case what you are measuring, is over maybe the voltage the operating voltage. Now you have to change the sensor, or you have to do what again?
Okay, if basically the input range of that particular sensor, they basically exceed the operating voltage. For example, your sensor is running at 5 volt. All right.
Yes,
And
yes.
initially you are not detecting any flow, any motion, anything. Your environment is not giving you any change. It stays down at 0. Suddenly, you see something, the reading starts to go up, up to where? Maximum.
Yes.
So it will stay until maximum, and it will give you straight line, nothing else.
Yes.
Okay, so your signal conditioner, your A to D, will basically receive maximum voltage, 12 volt. And from here, they will convert to the maximum voltage. For example, if you are using 4 bits, they will give you 1111, for example, representing the maximum things. All right, something like that. So in this case, you are receiving this. You may need to improve your operating voltage. You might need to use maybe 12 volt or something, or maybe you need to use different sensor, because you must know that every sensor, they have the transfer function, right? For example, for the temperature sensor, I may produce 1 millivolt per degree Celsius. in this case, I would give like 1 volt per Celsius. Okay. So now, if I have, for example, now if I have 1 degree Celsius, I will get 1 volt. Okay. So my graph will show me 1, 2, 3, 4, 5, for example. So if I have 1 degree temperature rise, I will have 1 volt. Now if I have 2 degree temperature rise, I will have 2 volt, because the system transfer function is this, the sensor transfer function is this. All right.
Yes.
So I have 1 degree Celsius, my sensor will give me 1 volt, which here. Now my temperature goes to 2, I have 2 volts. Okay, this is the time, this is the V. So I have now 4, let's say now I have 5 degrees Celsius, my system will give me 5 volt. All right. So now I'm at the maximum. So if the temperature keep on rising,
Yes.
I keep on getting 5 volt, because that's the maximum
Sensor.
power that I have
Operating
from my
voltage.
sensor. Yeah, so for this particular case, either you need to use sensor that uses more power supply, which is like 12 volt or something, or you need to
Oh,
find the sensor that basically use different transfer function. For example, 0.5 volt per Celsius, for example, or maybe something much more, very fine change, maybe point zero 0.01 volt per 1 degree Celsius. All right. So this is what you can do and what you can play around with the sensors. All right.
thank you, doctor.
All right. I hope I get it all right. Okay. These are the input signal. Okay. I will just move my pen so that I can get everything removed. So the next thing I have is the sampling rate. All right. This slide here shows something on the sampling rate. Okay, you can pay attention to this analog graph over here. I have analog signal coming from, for example, temperature sensor. I have the temperature rising at what they call that 12 p.m. and I have my temperature going down to negative 10 degrees Celsius, for example. This is plus 10 degrees Celsius at I would say 12 a.m. And then tomorrow morning my temperature goes up again. All right. So this is basically what my system is sensing. All right, in the analog form, a temperature profile for 1 day, for example. All right. So basically, I want my micro P or micro C or my data system being able to read this analog signal and convert into digital form. All right. Basically, these are the process that they have to go through in order to get everything into digital form. This is basically the first step. Okay, this is your input signal, and this is number two. You have the clock signal. Number three, when you impose number one and number two, you will basically get this number three, and this is after you do sample and hold, you will get number four. All right. So what happened at number one? Just now you see this is the information that I received from my sensor. For example, here again I repeat, this is my temperature reading in the morning, in the evening. For 1 day, right? Temperature goes up and down and up again. All right, this is, I think, all right, maybe somewhere in the Iceland or Greenland or something, you have this kind of temperature profile. Who knows? All right. So I need this is what basically you see in the analog system. All right, analog system meaning that the boxes, these two boxes before the A2D, the sensor and the what they call that signal conditioning box. All right, from these two boxes you receive this. All right, this is what basically you see when after these two boxes. All right, the signal that you're looking at now is basically the signal right before the A2D box. All right, A2D blocks. All right, so when the signal enters A2D, all right, number 2, number 3, and number 4 basically will be happening. All right, so graph number 2, you have the clock signal. Okay, the clock signal basically is a spike signal, it's a spike train signal. Okay, in which in between that you have the T. All right, this is the T, the time, the time, the time. All right, the time is fixed until you switch off the system. All right, so the clock signal basically relates according to a fixed timing. All right, and when you superimpose this analog signal with the pulse train, with the spike train signal, you will get the number 3 signal, in which you will have this kind of marking. Okay, where the clock signal and the analog signal basically overlap or collide or something. Okay, so you will have this kind of spike holding the voltage of of the analog signal at particular time. So this is let me remove this. Okay, this is T1, this is T2, this is T3, this is T4. So again, at T1, the chips or the A2D freeze the voltage information. Okay, for example, here I have, for example, I have 5 volt. All right, this is T1. Okay, this is T2. At T2, the voltage is at 0 volt. All right, I can simply pick up like that. And at voltage T3, the voltage here is I would say maybe negative 5 volt. All right, so this is what happened when you have analog signal, you superimpose with a spike train signal. Okay, which is the clock signal, and you will get sample signal. And when you send the sample signal into a sample and hold circuit, you will have something like this. All right, so this is still in the analog form. You still have maybe here 3.5 volt, this is 4.2 volts. All right, this is maybe 5 volt, this is 5 volt, this is 1.2 volt, maybe this is 5 volt. All right, things are still in the analog form. All right, you will not see 0101 at this particular stage. All right, but these are the process in the A2D. All right, in which I would want to tell you that sampling rate is referring to the clock basically signal that you send to the input that will result the graph will result to this graph. All right, so after sampling, you are basically receiving this at the end. If I have, for example, I give the same signal. If I have more spike train, okay, at the end I will have more of these boxes, basically, something like that. I have more boxes. Here I have 1, 2, 3, 4, 5, 6. All right, here I have more. Okay, so meaning that my sampling rate, okay, is of higher. For example, here, let's say the time is equal to 1 second. I have 1, 2, 3, 4, 5, 6. So this is 6 hertz system. Okay, as for me, this is time equal to 1 second. I have, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 11, 11, 12. So I have my system is 12 hertz. So meaning that if I have 6 samples per second, I only have I would say 6 reading per second. Okay, 6 number of reading per second, 6 sample per second. But if my system now is running at 12 hertz, I have 12 reading in a second. So okay, practically the more sample that you have, all right, the higher the sampling rate, okay, which refer to the hertz here, okay, the more accurate you have representation in the digital world. All right, so that's the rule. The more sample that you have, the higher the sampling rate. The more sample that you have, the higher the precision is for the system. Okay, so that's the rule that you have to put into your mind. All right. um I will leave that thinking for a moment. Okay, we have covered the input signal. We are talking about the sampling rate. Let me go through this thing. All right, you have humidity versus time, temperature versus time. All right, so these are the sample or sampling process that that this is basically real. You have time here, you have the humidity reading level over here. So this is what you get all over the day. All right, so the data acquisition process basically will result to something like this at the end, because I don't know, most of you, maybe you have your research project and all that. You may need to do some data collection. You may work on the system of instrumentation, and at the end of the day, you are looking at this kind of data over the time recording. All right. So again, this one, sorry, sampling. Okay. Yeah, we are basically here just now, sampling of analog signal, taking sample of signal discrete time. Yeah, I think we have covered this thing. Sampling rate, just now we were talking about, determines how often conversion take place. Coding, we are looking at hertz just now. For example, this is 4 sample per cycle. If cycle equal to 1 second, then you can get the number in terms of hertz. In this case, you have 4 hertz. In this case, you have 8 hertz. And here you have 16 hertz, meaning that you have 16 sample in a second. You have, in this case, 8 sample in a second, and in this case, you have 4 sample in a second. All right. Again, why you have so many sample that you can choose, but which one basically to choose? All right. You may have that kind of answer. Okay. You can basically pay attention to the graph here. Okay. You have the input graph. This one. This is your analog input. Okay. Again, I mentioned just now, the higher the sampling rate, the more information you will get, the higher the precision. Okay, if you look at this analog input, it's a pure sine wave. All right, but if you take only 4 samples per second, you will get these 4 points, and you will eventually end up with a square wave. Okay, you will basically end up with a square wave. Okay, if you take 8 samples per second, you may be ending up with you know, something like this. Okay, I redraw this thing for you so that you can basically see. For example, this is what happens if you take more sample but still not very much sufficient. What happens if you take 16? You may have, you know, something very much representing the original signal. All right, this is the signal that you get from the sensor that you are reading, in which of course you can only see this kind of response by using oscilloscopes. All right, from your sensor you can put on the probe, you can see the response in oscilloscopes. All right, but the main idea of what they call that A to D is basically to convert everything into the digital world, so that you can process using algorithms, you can process using programming codes, you can do a mathematical transformation and all that. All right, so it is very important in this process that when you do conversion, the information is preserved, the information is not lost. Okay, if you look at the first example here, number one, your sensors is basically reading sinusoid, but your A to D is not so efficient. They will give you square wave to the micropiece, so you have information loss here. Okay, this is misinterpretation of information, so it's totally crap. All right, if you look at the second one, you sample at a higher frequency but still not sufficient. You get something like sinusoid, but it is not sinusoid. Also, you know, information loss, and you know, you are not processing, you are not working on the real signal from the sensors. All right, because something is wrong with your sampling rate or sampling period. So what happens if you improve the sampling rate? You get something very much representing the analog input. All right, so that's why, you know, when you are working with data acquisition system, basically you need to be aware of information loss and precision in this case. Here this says that this rate at which the signal is sampled is called sampling frequency. Just now we have seen a few sampling rate, a few frequency, and basically what happens if you sample at the wrong sampling rate. You have, of course, information loss. Okay, but when you are working with your input signal, for example, you are working with a power line signal, which is you know, you want to do some collection on the power disturbance, for example, or some of you may be working with biomedical signal, some of you may be working with a noise signal, you know, radio frequency and all that. How do you select the best sampling rate? For example, if you select you know, wrong number or lower or higher, you know, you have information loss. All right, so what to do? All right, so this slide basically tell you something about the Shannon theorem. Okay, sampling rate is at least twice the highest frequency, so that the sample gives the original signal form on the signal. Okay, so they say here, if, for example, I take the power line. The power line is basically sinusoid, pure sinusoid. Do you agree with me? Do you know this or you don't, guys? Our
Yes,
power line,
doctor.
yes, 240 volts AC. All right,
Yes.
correct.
Yes.
So in Malaysia, the power line takes 50 hertz. Correct.
Yes. In
In
Nigeria,
some,
60 hertz.
yes, in some countries, 60 hertz.
Yes.
All right. So if you are doing data collection, if you are doing this kind of interfacing using the EQ, first, before you can determine the sampling frequency, you need to know the behavior of your input signal. Okay, in this case, my input signal, the things that I'm measuring now is power line disturbance. All right. So understanding the nature of my input signal, my my power line is basically running at the amplitude of 240 volts AC. with a frequency of 50 or 60 hertz. All right. In this slide, you can say that you can see they mention twice the highest frequency. Okay, so if my power line here is 50 hertz, so my sampling frequency is at 100 hertz. At least you can go beyond than that. You know, you can go 200, you can go 300. Is up to you. You can go all the way higher. It's more accurate basically, but you will have more information. More information meaning more storage. More storage meaning that more energy. Okay, so we go to the minimum. Because in this case, if my signal is at 50 hertz, if my input signal maximum frequency, my input signal can give me the maximum is 50, so I will sample at 100. All right. If my input signal is having its maximum frequency is 60 hertz, then my frequency sampling is at 20 hertz. For example, another example, my voice now, human auditory information. Basically, if I record my voice, if I look at the frequency spectrum, I'll see my voice maximum around 2 kilohertz. Okay, maybe Abdullahi, your voice is maximum only 1 kilohertz. Okay, so if I were to record my voice, I would choose sampling frequency of 4 kilohertz. If I were to record the voice of Abdullahi, I will just sample at 2 kilohertz. Will be sufficient. All right. So this is how you define sampling frequency for any system in DEQ. All right. You get it, guys?
Yes, doctor.
Thank you. So first, you need to understand your input signal. If, for example, you are working with biomedical signal, for example, your ECG or your brainwave. All right. You will have to understand what is the possible maximum frequency of the brainwave. Okay, maybe alpha, beta, gamma, and all that. The maximum is 7 hertz, so you sample at 14 hertz, for example. All right. Okay, sampling rate, aliasing. This is not very important. Basically, this is aliasing is some kind of effect that you may receive if you are sampling at the wrong frequency. Okay, as long as you know the maximum frequency of that information, and then you double the maximum frequency for the acquisition, then you are good. If you don't follow the rule, basically you will get rubbish from your signal, and you are just wasting your time because you are working at the wrong signal. All right. Okay, so that's very much on the input signal, and there's also some information on the sampling rate. All right, guys, you want to stop, or we can continue for another like 30 minutes or something? We can start and we can continue in 2 days. I can't be finishing everything by tonight. I still have I think more slides. I will need another session, because this is the main content of your master's level. I'm going through a bit slow and detailed for your understanding, of course.
Yes, doctor. It's all right, doctor.
Really, just Abdullahi all right, or everybody's all right? Because I know it's quite late now. It's 10:20. It's 10 almost 10:30. Yeah. Guys, any other? Yeah. Muhammad Najib say I'm okay. Yeah. So I'll take the word from. Turn your audio. Okay, to my Sarah. All right. Okay. I will continue. I have ADC. I have resolution. Okay, resolution will also take here. I'll finish resolution and can go to sleep, guys. All right.
Okay.
Thank you. So, analog to digital conversion, basically, Just now, you know about the input signal, in which the input signal is a signal that come from your sensors. That after that come from your signal conditioner. Okay, it varies from 0 volts up to the maximum operating voltage of your instrumentation system. If the operating voltage is 5 volt, your input signal is just from 0 to 5 volts. If your operating voltage is 24 volt, your input signal is from 0 to 24 volts. All right. And after that, we also look at the sampling frequency. Now it is very much defined by number of sample that you receive in a second. We also look at a different number of sampling frequency, and what kind of effects you can observe from your signal. Okay. And you also know that the higher the sampling frequency, you will have more information that will basically improve the precision. All right. But at the same time, it means more storage, because you have more data per second. And of course, more storage meaning that you have to work on higher processing, and which you will need higher amount of energy to work with. All right. So so that's basically input signal and sampling. Now we really go to the conversion of from analog to digital. From this graph, you can see that this side is basically on the analog side, and this side is basically on the digital side. Okay. Okay. In the analog side, basically you have voltage maybe running from minus 5 volts. Sorry, I got it wrong. Here in this case, basically you have from 0 volt, okay, going up to 1, 2, 3, 4, 5, 6, 7 volt. No, 111 is basically it doesn't matter. Basically, you can basically choose any volt. You can basically put 10 volt over here. Okay. What happened is that this is analog. You want to convert into digital. Okay. What will happen is that depending on your sampling rate, also, which basically represent how frequent you acquire the signal, how frequent you sample the signal. Okay. And also, one more thing you have to know when you work with ADC is that the resolution. Okay. It says here in this text, the digital number represents the input voltage in discrete steps with finite resolution. Okay, ADC resolution is determined by the number of bits that represent the digital number. In this case here, you have 3 bits. Okay, all the way up, all 3 bits. Okay, so in ADC, now you are looking at input signal. You already look at sampling rate. Now you are looking at the new terms called resolution. Okay, resolution here define the number of bits that you use to represent your analog voltage. For example, here I have 1 volt. This is 2 volt, 3 volt, 4, 5, 6, 7. Okay, 7 volts. All right. So now, if I can pick up from this diagram, I have 1 volt represented by 001. So if I take 2 volt, now I am going to get 010. Again, if I have 3 volt, I will basically get 0, 1, 1. Okay, this is analog, this is digital. Okay, so how do I get from here to here? Basically, resolution. Okay, we will basically going further to understand this, but this is what happened when you convert analog voltage to digital representation. Okay, from this diagram also you can see this is your analog graph. Okay, when you plot at the same plane of analog and digital signal, you are looking at the mapping between analog to the digital, and this is how basically the conversion happen. If you take 1 volt, you will get one representation. If you take 2 volt, you will get something like this. Okay, so now 011 is representing my signal at 3 volt. 010 here is representing my signal at 2 volt, for example. So I have like this. This is 3 bits, 3 resolution. When I use 3 bits, I can only have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. I can only get 8 levels. Okay. For example, here 0 to 7 volt. Okay. When I convert information from 0 to 7 volt, any kind of information, okay, when I convert into analog, I will have information up to 8 level, 0 to 7. 0 itself is considered as a level, so I will have conversion using this marking point. Okay, if you take 7 volt, you divide by 8 level, you will get what? Can somebody get that for me? 7 volt, you divide by 8 level, berapa dapat? Can somebody help me here? Berapa? 0 point berapa?
0.875.
So you will have 0.875 volt, meaning that this is 0.875 volt. Multiply by 2, 0.875 multiply by 2, berapa?
1.75.
1.75, and so on. You can multiply by 3, 4, 5, but when you multiply by 8, you will get the maximum there. All right. So meaning that if you are using 3 bits resolution.
Actually, I don't get this thing you did something.
Again.
I didn't get this actually. This division. I don't know how we got it.
Okay. Again, sorry, Abdullahi and everybody. My 7 volt is my operating voltage. Okay, 7 volt here you can imagine as the operating voltage of your sensor and your signal conditioner. Okay, if my operating voltage of my signal conditioner is 12 volt, then I will have 12 volt here. Okay, this is the maximum that I'm feeding to the ADC. Okay, from 0 to 12 volt, my signal can be anywhere, up and down, you know. For example, here from 0 to 12 volt, my signal can be anywhere. Okay, so I'll take the maximum range. I'll feed everything to the ADC. Okay, so this is why I have 12, the number 12 here. Okay, if my system is working on using 5 volt, I will have 5 volt over here, because the full information I have is up to 5 volt. I'm giving everything to convert. All right. But the level here, which is very much called as the resolution here, okay, it's depending on the number of bits. For example, you have three bits, okay, 0, 0, 0,
Yes.
okay, 0, 0, 0, 0 here represent the lowest point, which is 0 volt.
Yes.
Okay, so from 0, 0, 0, you can move the logic up to maximum 1, 1, 1. Okay, if you get from 1, 2, 3, 4, 5, 6, 7, 8, you have only 8 representation in the analog world, sorry, in the digital world. Meaning that the 12 volt that you are giving, all right,
Yes.
you have only 8 space to keep it.
Yes.
Only 8 levels. Here, 8 levels by the address of 0, 0, 0, 0, 0, 1 up to 111 here. You have only 8 storage. You have only 8 place to capture your analog signal. So you give 12, but they only keep 8. So 12, you have to divide by 8. Then you will see at each level, basically, they capture 0.87, 0.88. This is the actual voltage that this guy is capturing. So by the address of 001, they are capturing all information at 0.87 volts. Will be capped at the address 001, for example. Okay, so because the capturing elements here, okay, basically depending very much on the resolution here. If I give you 3 bit, I will have 8 storage. If I give you 4 bits, I will have 16 storage. If I give you 16 bits, I will have what happened? Oh no.
56.
Yeah, I think no. Where is it? Yeah, I think we are here. Okay. Yeah, if I were to give 16 bit, okay, this is number of storage that I'm basically receiving. So if I give you the bit, it gets higher and higher, I get more storage. And from here, you can basically see the number of storage here will follow this 2 to the power of 3. This is 2 to the power of 4. This is 2 to the power of 16. Because we are working with bits, we are working with binary, so that's why we are having 2 over here. Okay, did you get it, Abdullahi? Yes. No. So this is the number of storage. The more storage, the higher the bits, the more storage, the higher the precision. Okay, if you can refer to the sampling rate just now, the higher the sampling rate, the higher the precision and more data that you basically receive to represent the original signal. The same with resolution. The higher the resolution, the higher the precision. Okay, 3 bits, is super low resolution. You'll get nothing from it. Okay, only a fool people will use 3 bits in their ADC. These days around we have 64-bit ADC. 2 to the power of 64. How much is it? How much storage? How much precision we are talking about here? How many levels here? Okay, but before 16 you have 2 to the power of 32. Okay, So meaning that, you know, the higher the bits, the more storage you have, the more accuracy you will receive. All right. Do you have question, guys? No. Okay.
Yes, we are okay, Doctor.
Yes, I will basically continue. So this slide basically define the resolution, the effect of choosing the wrong resolution for your system, for your ADC system. For example, here you have very nice analog waveform. Okay. For example, you use ADC with 2-bit resolution. Okay. 2 bits meaning that you have 0, 0, 0, 1, 1, 0, 1, 1. You have only 4 levels. 1, 2, 3, 4. 4 levels. This is 3-bit. 3-bit, 4 level. Okay, I'll write it this way. This is 3-bit. You have 0, 0, 0 up to 1, 1, 1. You have 8 level. Okay. What about 5? 0, 0, 0, 0, 0 up to 1, 1, 1, 1, 1. Correct? So you have 32 level.
Yes.
Okay. So you can see that the higher the bit, you will have more storage, you will have more level, the precision improve. All right. You can represent your input data here correctly by using a very high resolution, very high conversion bits. All right. Again, just now, if you go back to the sampling rate, the higher the sampling rate, the higher the precision. But the problem is you need to provide storage. You need to provide bigger space in your hard disk, for example, to store more information. The same goes to the resolution. The more bits, of course, you can see here much more accurate, but you will need to prepare bigger storage because your one information that you receive from your sensor, okay, if you represent using a 2-bit system, you need to you need to prepare only 2 space because you have 2 bits. You have bit number 1, you have bit number 2. So for one data that you record from your sensor, you need to prepare 2 bits in your hard drive to represent one sample. But if you go for the 5-bit system to represent one data that you receive from your sensor in the analog world, in the digital world you have to prepare 5 spaces because you have 5 bits. 2-bit, 2 spaces. 5-bit, you have to prepare 5 storage, 5 slot in your hard drive. All right. Just imagine if you work with a system of 64-bit. One information, 64 space in your hard drive. So this is 64-bit. Okay. So sampling frequency, sampling rate, the same as resolution. The higher, the better. But then you have to prepare more storage. All right. So this is resolution. Yeah, this slide basically summarize what we have seen just now. Yeah, okay. What I want to do here is this one. Okay, you may have seen from previous example, guys. If I have my operating voltage is at 12 volt, okay, and my ADC is 5-bit, 2 to the power of 5, so I get 12 volt divided by 32. How much do I have here? Guys, can you please help me? 0 0.2? 0
0.375.
0.375. meaning that every 0.375 volt, the ADC will capture one signal and store at the right level, for example. Okay. Okay, guys, I want to show you how this kind of things affect your precision. For example, I have 12 volt system. Now I'm using a 3-bit system. Okay, to the power of 3. I have now 12 volt. I have 12 volt divided by 8. So what do I have here, guys?
1.5.
1.5 volt. Just now I have the same system running at 12 volt. This is 1, this is 2. But I have now the higher precision. I have 2 to the power of 5 bits. Alright. So I have here 12 volt over 32. So I have 0.375 volt. Alright. So here they say that if I have my signal, you know, something like this, at every 1.5 volt, this is 3 volt, then you will have 4.5 volt. All right, meaning that for my signal here, I will only capture these 3 points. Okay, everything in between will be ignored. Okay, because my system is only sensitive up to 3 bits. My system is only sensitive at this exact point of voltage. If I receive analog signal at 1.5 volt, I will capture. If I receive at 0.7 volt, I don't care because I cannot take it. Okay, the system can only take analog signal which match this voltage. Okay, which we have calculated. 1.5 volt, I'll take it. 1.7 volt, I don't care. Meaning that we only have these 3 values for this kind of signal, and the rest we will basically remove. All right, and we don't care basically. So in this case, we have a lot of information loss. Okay, if you compare to this one again, okay, at every 0.375, what next? 0.7 something.
75.
0.75. I capture the next one. The next I capture is what? 0.3 times 3, 0.125.
1.1.
1.125.
1.25. 125. All right. So you can see, guys, the higher the number of bits here, the more precise my system can capture. Just now, if you look at the system, I can capture only signal at this particular voltage. Okay, if you give anything lower or higher or in between, I will ignore it. So I will just get information at this voltage. Okay, which is 0 to 1.5, range of 1.5 volts. Anything between will be lost. Okay. For example, to make things look clearer, this is 0, this is 1.5 volt. Okay. For example, this is your information from your sensors rising from let's say this is 1 second, this is 2 seconds, this is 3 seconds, this is 4 seconds, and happen to be your signal is at, oh my god, I'm changing the brush. Your signal is at the 3rd second. Okay, so what happened is that when your temperature, when your sensors start to give reading, okay, you can only capture the voltage at this voltage. You can only capture information at this voltage, which is this voltage, which exactly on the 3rd second. Did you get it, guys?
Yes.
You are recording from 0 second to the 4th second, but because of the precision that resolution that you are using is 3 bits here, you only start recording at the 3rd second. So you miss information at the 1st and at the 2nd second.
Yes.
Okay, different with when you use higher bit resolution. Okay, for example, 0.37 volt is here, 0.7 is here, 1.12 is here. So meaning
Yes.
that at the 1st second, even in between that, you can basically capture, the changes, the information coming from your sensors. All right. So by this 1 and 2 example, I think that the higher the bits, the higher the precision, and it is very much proven by this kind of example. I think. I hope you guys can understand and capture this. All right.
Yes.
Thank you. This is exercise you want to try. They are answer down there. An ADC with a word length of 10 bits. All right. If the input analog signal range is 10 volts. All right. What is the resolution of this ADC? Can you guys do this? No. No.
What's up?
So you have 10 volts. So you have 10 bits. So what to do? Divide by 2 to the power
10.
of 10.
Those
So
by
10
10.
volt. So what is this? What is underneath here? How many levels?
It is 0.0097.
0.0009.
097, yes.
Correct?
0.123. 0.00976.
76.
Yes.
So this is the resolution. This is the precision of the thing. But you have to find the number here, guys. All right. Here they give you 9.8 millivolts. All right.
Yes.
So meaning that in every 9.8 millivolts changes, you will get the representation in the digital world. Okay. Here you have some definition of bits. On and off. I hope you get this just 0 and 1. Okay. In the digital world, okay, you will have only 0 and 1. You don't have voltage. All right. You don't have voltage. 0 meaning that 0 volt. 1 meaning that 5 volt. So only two things. So we don't say this is 5 volt, this is 0 volt. We say 0 or 1. If you get 0, you know this is 0 volt. If you get 1, you know this is 5 volt. All right. Then just now you have some definition of bits, which represent the single digit of 0 or 1. The next one you have byte. Bytes is basically a group of 8, I think. Group of 8 bits. You put them together, you call it 1 byte. Okay. If you have, of course, if you have 8 bit or 1 byte, you will have 256 different levels. All right. So here is the some kind of definition and conversion. 1 byte is equal to 8 bit equal to 2 nibble. This is 1, 2, 3, 4. You have 1 nibble. This is another nibble. All right. So 2 byte is 16 bit. Here you have 1 byte, 8 bit. 1, 2, 3, 4. 1, 2, 3, 4. This is 1 byte. If you have 2 byte, 1, 2, 3, 4. 1, 2, 3, 4. You will have 16 byte. All right. So 4 byte. Then we can basically do this. Okay. This is the very basic conversion. I think we have covered this just now. Okay. Correct. So you know how this thing actually map to the analog voltage. Go, these are all just encoding. Okay, so you know how to do this, right? For example, this is just things that work in reverse, basically. You know, if I have 5 volts here, okay, which basically represent by decimal as 255. 255 is represent the bits. I think 255 is equal to 8 bit. Okay, that's why you have 8 bits here. So 5 volt in the analog world, okay, because you are using 8 bit, you are working with 255 level of decimal. Okay, in which if you convert to digital, you will be having 010101, and maximum is 1111 1111, which goes back to 255. Okay, so you can work on some ratio here. The maximum in decimal is this. If your signal is 1.2 volt, you have to divide by the maximum things here, and the maximum goes this way, and basically you will get 61.2. In decimal, you have to remove the floating point. You go to 61. If you convert to what they call that digital, you will have this sequence. Okay, so the same goes with 3.7 here, goes this way. The maximum goes here, because this is some kind of ratio, 3.7 over 5, so you will have something over 255. So 255 here is the maximum decimal, which is equal to 5 volt. In the analog world, you will have this value, you round up to this one, and you will get this one. Okay, this is how you convert from analog signal with respect to its operating voltage. Just now we have go through this, and how things are being done to convert the things into the digital punya format. All right. Any question, guys? Because this one kita tak go through in detail. Any question on this thing? Basically, you can. This is decimal. You can use your calculator to convert 61 decimal. They will basically show you this. All right. Yeah, I think. Yeah, this is the binary system, the numbering system. Okay, I will not go through in detail in this. This thing will not be asked. Wow, there are still this thing coming in. It's okay. So I think I'm gonna stop basically there. All right, for tonight. So I have to recap so that you know what we have been talking about from the beginning. Basically, we are talking about ADC, which very much come from the simple system of instrumentation. The simple one receive one input and give you one output. All right. The not so simple one, basically you will have multiple input and you may have multiple outputs. All right. And from there we are looking at the DAQ boxes 1, 2, 3, 4. One is signal conditioning, one is transducer or sensor, 2 is signal conditioning, 3 is ADC, and 4 is the display or processing box. All right, 1, 2, and 4 you have seen previously in the previous lectures. Tonight we proceed with number 3, which is the ADC, and going towards ADC, we have seen the input signal definition in some examples. We have seen sampling rate definition in some examples. We also have seen the next important element, which is the resolution, and what is the the conversion between the analog to digital using this kind of information. I have question here from Muhammad, I think. Muhammad says sampling rate is on x-axis, while resolution on the y-axis. Sampling, yeah, you can put it that way too, Muhammad, I think, because sampling rate basically works on the time. So time is normally stays in the x-axis. Resolution works on the amplitude, and amplitude usually stays in the y-axis. You can basically assume that, yeah, there won't be any problem with that. Thank you, Muhammad. Do I have some other question, or we can basically stop the thing? Guys, any other question, guys? We will have one more, what they call that, one more engagement, I think, at least last one, because I have prepared the test 2 question. All right, so I need to go through some of the exercises before you can answer those questions. Okay, so I'm gonna need one more class, which basically I will announce in the WhatsApp. All right, hopefully you'll be free in 3 or 4 nights, 4 coming nights. All right. Do we have more questions? No.
Yes, it's all right.
Okay, so I think that's maybe all for tonight. Okay, guys. Thank you very much. I'll see you again in the next few days. From there, I will try to get you prepared for test 2, the instrumentation section. And of course, I haven't give you guys the assignment things. All right, I know we are having a very little time. I'll figure out something which you can finish fast. All right, guys, don't worry, I'll take care of that.
Okay.
So okay, guys, thank you very much. I think that's all for tonight. Stay safe. The COVID-19 case currently, on the rising end. We don't know how long we are going to have to deal with this. Hopefully everybody, take care of yourself. All right. Good night, guys.
Thank you very much, Dr. Masala.
Thank you, Doctor. Salam
alaikum. Have a good sleep. Assalamu alaikum.
Alaikum salam.
Thank you, Doctor, very much. Thank you.
Thank you.
Assalamu alaikum.
Alaikum salam wa rahmatullah. Thank you very much.
Thank you.